All right, death packet. These are problems 41 through 50. So a linear regression analysis relating secretary salaries to years of experience yields the following, where X is the years of experience and Y is the salary. Which of the following is the most proper conclusion? A starting salary, a starting secretary will earn $19,780, while one with 70 years of experience should earn $180, whatever. The very fact that they say that they will earn this amount, I don't like that phrase. We predict that they will earn that amount. On average, they will earn that amount, but we don't know that they will earn that amount, because remember, we are modeling a scatter plot of data. So we have a data line, but we have some people making more, some people making less. So it's all over the line. So there's no guarantee that they're going to start there, but that is the average that they will start at. So I don't like A because they say will start, will earn, and it's like, no, on average, we expect them to earn, all right? It says starting salaries will increase in averages. No, they won't increase in average. They're going to increase an average of 2,405 a year. That's not, I don't know where they came up with this bonus part. That just doesn't apply. There is a cause and effect. There is no cause. We don't like that. Starting salaries for secretaries is an average of 19,070, and each year of experience is associated with an average increase of 2,405. Some is going to be less, some is going to be lower, because we're dealing with a scatter plot of data. So D is our best answer. All right, number 42, data from a simple random sample of property owners is cross-classified by gender and support for a new educational initiative and given the following table. Is there evidence of a relationship between gender and support? I see the word relationship. Oh, that's a key word. All right. And also when I look at this, I'm like, you know what? I have multiple categories. Multiple categories tell me it's a chi-squared. I see relationship. I see independence. So here's what I need to do. I need to be really cool and enter the matrix. Or try to. You're like, why did you do one by one? Because I wanted to get rid of a bunch of data. So two enter, and I have 35, 45, 55, and 50. All right, so I've entered the data, and I'm going to go stat test, and this is a chi-squared test. So letter C, it's not as a goodness of fit. If it had been a goodness of fit, I'd either have one row or one column. I don't have that. I have 2 rows and 2 columns. Matter of fact, given this, I know my degrees of freedom is going to be, in this case, rows minus 1 times column minus 1. So my degrees of freedom, 2 minus 1 times 2 minus 1, degrees of freedom, and move 1. Calculate this thing, and I ended up getting a p-value of 0.244. So with a p-value of 0.244, let's just say we compare that to an alpha of 0.05. Well, this is greater than 0.05, so I'm going to fail to reject. Now, there's always evidence. I have evidence. I just don't have enough evidence. All right? So we have weak evidence. All right? We can't say there's no evidence. There's obviously not strong evidence, because if there's strong evidence, we would reject. But we have evidence. We never say there's no evidence. We have weak evidence. All right? So there's a weak evidence of this relationship. All right. 3 professors are interviewed as to a sampling of their grades, and the following tables give the resulting counts. A statistics student runs a chi-square test of homogeneity. What is the proper conclusion? All right, so first off, if they hadn't told me this was a chi-square test of homogeneity, I'd like to address what I know. I know for a fact I have multiple categories. is going to be a chi-squared. All right. I know it cannot be a goodness of fit because I have more. I don't have just one row or just one column. I have multiple rows and multiple columns. Therefore, it's going to be a chi-squared test. And I might have difficulty knowing whether it's independence or goodness of fit. I mean, independence or homogeneity. And it would depend on what they said. In this case, we have multiple professors. So we have basically, depending on how they collected the data, would depend on whether it's independence or homogeneity. If they say this is one population, this is a population, and this is a population, it makes it homogeneity. But they told me it was homogeneity. So I'm going to go ahead and run this test. And I'm going to go stat. I'm going to enter the matrix, second matrix. We have a 3 by 3. So I'm going to enter that data. Sorry for the dead airspace. So I've entered the data, and I'm assuming it's a random sample. I don't know if it really is or not. I notice that these are all whole numbers. That's good. And I'm going to go ahead and run this test, stat test, and chi-squared test calculated. And I end up getting a p-value that's at 0.086. So that's less than 0.05, but greater than 0.01. That's probably important to know. But I'm going to go back and look at things, and I'm going to look at my matrix real quickly. And I notice that I have expected values that are less than 5. We can't run a test if expected values are less than 5. So while this appears to be statistically significant, it was not appropriate to run the test because our expected values were less than 5. If they'd been greater than 5, then we could have said that there was evidence at some level, but because they were less than 5, we can't run the test. All right, number 44, this is probably a problem you should put a star by. So a highway superintendent states that 5 bridges into a city are used in the ratio of 2, 3, 3, 4 during the morning rush hour. So that's the ratio that they're claiming. A highway study of a simple random sample of 6,000 cars indicated that 920, 1,570, 1,480, and 2,030 cars use the 5 bridges respectively. Can the superintendent's claim be rejected? So they want to know, this is the observed. They observed this, 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 and this. And they want to know whether or not it fits that. First off, let's do something real quickly. This is why you said you should probably start this problem. All right. So 2 plus 3 plus 3 plus 4 equals 12. So this is 2 out of 12, 3 out of 12, 3 out of 12, and 4 out of 12. This is my column of, this is my observations. I only have one set of observations. If I only have one set of observations, although I have multiple categories, I have 1, 2, 3, 4 categories. Although I have multiple, I have 5 categories. I have this one. Sorry. No, I have 4 categories. 1, 2, 3, 4. 4 categories. Although I have multiple categories, which tells me it's a chi-squared, because I only have one list of data, this is telling me it is a goodness of fit. Plus, they're trying to see if it matches what someone is claiming, the claim distribution. Does it match this distribution? So here we go. We're going to go to the stat edit. I'm going to clear out a bunch of stuff because I have a bunch of stuff in there from working with the regression part. And I'm going to put in my observed data. So 920, 1570, 1480, and the 2030. That's my observed data. Now, we know we're working on this. these are what they're claiming. So I'm gonna go ahead and put this in 3, enter, 3, enter, and 4, enter. But this is really 2 out of 12, 3 out of 12, 3 out of 12, and 4 out of 12. And there's multiple ways to do this, but I'm just kind of gonna go hot, kind of cheat, because I could have just put 2 divided by 12, 3 divided by 12, 3 divided by 12, or 4 divided by 12. To be fast about it, I'm gonna go second 1 and divide it by 12. But again, excuse me, I did that wrong. Very nice. 2, enter, 3, enter, 3, enter, 4, enter. Second 2 divided by 12. There we go. All right, so that's just 2 divided by 12. 3 divided by 12 is 0.25, 0.25. So that's my ratios. That's what we're expecting. That's the percentages we're expecting, but we had 6,000 cars. So my expected value is N times P. So it's going to be 6,000 times the percentage. So 6,000 times each one of these values. So I'm going to go all the way back up there, the top, and I'm going to go second 2, L2, times the 6,000. And so that's how many cars I would expect for each one of those. And that should sum up to, 6,000 if I've done everything correctly. And that's 2,500. Yeah, that sums up to 6,000. So we have expected values in. We have our list of expected values. And I'm going to go stat, test, goodness of fit, because we're matching a previous distribution. Degrees of freedom, we have 1, 2, 3, 4 categories. So degrees of freedom for a chi-squared goodness of fit is cat minus 1. So in this case, 4 minus 1 or 3. I'm going to have it calculated. And it gave me a p-value of 0.015. So 0.015 is less than 0.05, but it's greater than 0.01. So I'm rejecting at the 0.05 level, but I'm failing to reject at the 0.01. And so they want to test it at the 1% and the 5%, not at both. And by the way, if there's evidence to reject at 1%, then there will be at 5%. So that's never going to be an answer. There's sufficient evidence to reject the claim at the 5% level, but not at the 1%. And that's where we fell. We could reject here, but not here. So our answer to number 44 is C. Number 45, a study of accidents at a large factory reported the following numbers by shift. Is there sufficient evidence to say that the numbers of accidents in the shifts are not the same? Well, first off, I have more than 2 categories. More than 2 categories, chi-squared. 1 row of data, GOF, goodness of fit. All right? Or technically, 1 sample, 1 variable. So here we go. They want them to be the same. So I need to add all these up. 35 plus 77 plus 53. So I have 165. And I divide that by 3. And so if they were all the same, if they were supposed to be the same, I would expect there to be 55. And I did that by totaling this and getting 165 for my total. And these are just 165 divided by the 3 categories. So I'm going to go back to stat edit because I love it so much. Stat edit changed my life. I bet it can change yours. My observed values is 35, then 77, then 53. My expected value is 55, 55, 55. Stat, test, chi-squared, goodness of fit. Observed, L1, L2, degrees of freedom, 1, 2, 3. Remember, it's cat minus 1. So we have 3 categories, so 3 minus 1. And I ended up with a very small p-value. 0.0003 is my p-value. All right. And I have sufficient evidence. I'm rejecting, so I have sufficient evidence at the 0.001 level. All right, on number 46, to compare prices at a grocery store in the suburbs with one in the city, a housewife picks 10 basic items and checks the prices of the numbers at each store. Which test should be determined? So basically, we're choosing 10 items. I don't know what they're choosing. Artichokes, squash, something very important, Coca-Cola. All right. And I made a list of them, and I have 10 items. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's like they're buying artichokes at store A and store B. And so they have a price here and a price here, and a price here and a price here, a price here and a price here, price here and a price here. All right. So in this particular case, we're testing something twice. We tested the artichoke price twice. We checked this compared the squash price twice. We compared the Coca-Cola price twice. So this would be a matched paired t-test. All right. And you're like, well, wait a second. Couldn't it be we have multiple categories? Couldn't we look at this as multiple categories? It's like you could, but then the question would have been different. You could sit there and go, well, is the distribution of one store match the distribution of the other store? If they said the distribution of one matches the distribution of the other, it would have been a goodness of fit. If they said it does price vary depending on the store, and it's like, I want to know if they're independent. If I want to know if there's a relationship, then it'd be independence. But here we're just checking prices, and something was tested twice. Artichokes were tested twice, squash were tested twice, coats were tested twice. So this would be a matched paired test. Pretty challenging problem if you ask me. So number 48. A geneticist claims that 4 species of fruit flies should appear in the ratio of 1, 3, 3, and 9. Again, this is one you probably should star. And if I added these up, 10, so 16. So this totals out of 1 out of 16, 3 out of 16, 3 out of 16, and 9 out of 16. Those are proportions. So we have 480 flies, and they contain 25, 92, 68, and 295. Does the chi-square test show sufficient evidence to reject the geneticist claim? So I have one sample, and these are my distribution. They want to know, does the distribution match? And because there are multiple categories, that tells me it's a chi-square test. Because they want to know if the distribution matches what is claimed, it should be a chi-square goodness of fit. And we only have one row of observed data, so that also confirms that for me. So with that said, I put in 25, 92, 68, and 295. And just so I don't mess it up, 1 divided by 1, 6, 3 divided by 1, 6, 3 divided by 1, 6, and 9 divided by 1, 6. Now that's my percentages. And remember, expected value equals N times P. Well, we had a sample of 480, so I need to come back and multiply that entire column by 480. So I'm just going to press second 2, that's column L2, times the 480, and that gives me my expected values. All right, and notice they're all greater than 5. I can go ahead and run my chi-square test. Stat test, we said is a goodness of fit test. Degrees of freedom, 1, 2, 3, 4 categories. So cat minus 1. So 4 minus 1, so we have 3. And I end up being 0.035. All right. So, by the way, test proves the claim. In no hope, we never ever prove a claim. We don't, we're just haters. We either reject it or we reject something and choose something else. The test proves the genetics claim is false. Once again, we don't really prove anything, or that's a possible answer, but let's see if there's a better answer. The test does give sufficient evidence at 0.0, because we ended up with a p-value. Our p-value is 0.035. That's less than 0.05. So we can reject at the 0.05 level. All right, so we can reject. So it does give sufficient evidence. The test gives sufficient evidence to reject the geneticist's claim. This is the best answer because we really don't prove anything. All right, we get enough evidence to suggest something, but we're never 100% certain. In other words, there's always a chance we could be wrong, and basically at the 0.05 level means we don't mind being wrong 5% of the time. So it's possible that we are wrong, but we have enough evidence that we are choosing to reject. All right, number 49. The table below shows the number of students referred for disciplinary reasons to the principal's office broken down by day of the week. The counselor would like to know if such referrals are related to the day of week, what is the value of the chi-square for the appropriate test? Well, first off, I need to sum these up. And that, I mean, that's just always a good place to start. So 12 plus 5 plus 9 plus 4 plus 15 totaled up to 45. So we ended up with a sample size 45. So this is our total. And we have 5 categories. So, and they want to know basically whether or not it's the same for each day of the week. Is it related? So we're going to go 45 divided by 5 is 9. So I'm expecting it to be the same for each day of the week. So with that being said, remember our formula, chi-squared equals observed minus expected squared over expected. So our second number should be 9, and our denominator should be 9 for all of these. So B. Now, some of you are going, hey, is it related? That's like an independence word. And you're right, that is an independence word. So you're going, could this have been a chi-square test of independence? And the answer is no. Because the easiest way to think about it is, yes, I have multiple categories, which tells me it's a chi-squared. But remember, we have to have multiple variables, and I only have one variable, which is referrals, all right? Or more technically, or not technically, less technically. So this is one sample, this is one sample, one variable, goodness of fit. That's the technical. The quick and dirty way is multiple categories, chi-squared. One row or one column, goodness of fit. One row or one column, goodness of fit. So this is a goodness of fit because I only have one row of data. And you're like, well, why does that really matter? Well, to be either a homogeneity or independence, the degrees of freedom has to be row minus 1 times column minus 1. And I only have one row. 1 minus 1 is 0, so I'd have 0 degrees of freedom. That makes no sense. All right. Hope that helps a little bit. Okay, number 50. Which of the following is the proper use of a chi-square test of independence? A, to test whether the distribution counts on categorical matches a claim distribution. So we're looking for independence. Matches a claim distribution. This is a GOF. All right, and we're looking for independence. Again, we're looking at GOF. All right. Continuing on, to test whether two categorical variables are, here's our key word. We like categorical. This is what we're looking for, categorical. Actually, I shouldn't have liked this because it was numerical anyway. We're to be a chi-squared is working with categorical variables. And this one is to see if two categorical variables are in fact related. Okay, so the question was asked, the difference between a categorical and a numerical variable. Categorical variable is a description, and so it puts you into a group based on a description, but quite frankly, there's really not a normal order to it. Blue eyes and brown eyes, which comes first? Numerical is going to have a specific order to it, whereas categorical will not. All right, so a small appliance manufacturer sets up 3 locations to provide service for its customer. Logs are kept noting whether or not calls about the problems are solved successfully. Data from a sample of 500 calls are summarized in the table below. Assume there is no association between the location and whether or not a problem is resolved successfully. What is the expected number of successful calls solved from location 2? All right. So expected number of calls from a problem solved from location 2. So I'm interested in this, and I'm interested in that. Now, really, I should go ahead and total the entire column, total everything, but I'm just going to total the things that I'm interested in. I'm going to total location 2 and problem solved. So problem solved was 124 plus 98 plus 103. So this is 325. And this is 98 plus 63. So this is 161. So this totals to 161. Now, if I were running this and they were independent, if they were independent, I would go 161 times 325. This is what I'm expecting, divided by the total, because that's what the calculator is actually doing behind the scenes when it calculates when we enter the matrix, that's what it's doing. The row total times the column total divided by the total. All right. So 161 times 325 divided by 500, the answer to 51 is E. By the way, 52 is probably my favorite problem in the entire death packet. In the following table, what value results in a table showing perfect independence? If things are perfectly independent, that means there's no relationship. Remember, perfect independence, no relationship. And if there's no relationship and they're perfectly independent, they are proportional. All right, so in this case, 40 over 50 equals, I always feel smart when I do this problem. 40 over 50 equals 60 over X. So obviously 50 times 60 divided by 40. And so X, or in this case, N, equals 75. Love that problem. I actually feel smart right now. All right. So 52 makes me feel smart. 53 makes me feel dumb every single year. I always have to read this problem 3 times in order to do it. And the reason I'm doing it relatively rapidly now is because I've read it 3 times already. So 2 commercial flights per day are made from a small county airport. By the way, that's key. The airport manager tabulates the amount of on-time departures for the sample days of 200 days, okay? What is the chi-squared statistics, for goodness of fit, oh, nice of them to tell us that the distribution is binomial with a probability equal to 0.8 that a flight leaves on time? Well, binomial. So 2 flights a day, 0.8 to the 0.2, and we're going to do that. And then we're going to do 2 choose 1, 0.8 to the first, 0.2, and that's also to the first. Then we're going to go 2 choose 2, 0.8 to the 0.2, 0.8 to the squared, and then like that. So that's what we're going to do. So here we go. Let's get those probabilities. And remember, we can do that second vars binomial PDF. Trials is 2, P is 0.8, X value 0. So my percentage is 0.04. Then I'll do the next one, second vars binomial PDF. X value this time is 1. And I get a percentage of 0.32. And then I do the next one, second vars binomial PDF. X value is 2. And I end up getting 0.64. And notice those sum up to one whole. All right, that's great. We now have our frequency. And remember, our expected values equals n times the probability, or expected value equals NP. N in this case was 200. So it's going to be 200 times 0.04, which is 8. Then we're going to have 200 times 0.32. And then it's going to be 200 times 0.64. So these are my expected. These are my expected for 0, my expected for 1, my expected for 2. And remember, our formula chi-squared equals observed minus expected squared over the expected. So my number for the first one, my first contribution, the numerator should have the expected as an 8 and an 8. That's right there. And there's my observed, and these are my observed. Then it'd be 75 minus 64 divided by the 64, and then the 113 minus the 128, and it should be there. All right, so the answer to number 53 is A. And like I said, that one always makes me feel dumb. All right, number 4, which of the following is not true with regard to contingency tables for a chi-square test for independence? Categorical rather than quantitative data are being considered. In other words, they're saying not true. Well, this is true. Observed frequencies should be whole numbers. That's one of our conditions. That's true. Expected frequencies should be whole numbers. That's false. They don't have to be. They have to be greater than or equal to 5, but they do not have to be whole numbers. All right. So that's so C is the answer to 54. All right, number 55. Is the preference between vanilla and chocolate ice cream independent? Multiple categories, multiple rows, multiple categories, chi-squared, and then I have multiple rows and columns, and they ask for independence, chi-square test of independence. So we need to sit there and test this out. So we're gonna have to enter our matrix. So second matrix, edit, enter, and we have 1, 2, 3, 4, 4 by 2. I'm gonna get rid of that stuff first. There we go. Oops, I'm sorry. 2 by 4, rows times columns, I know that. 22, enter, 31, enter, 21, enter, 40, enter. Since I can hardly see those, I sure hope I input those correctly. Like, how come you can hardly see them? Because I'm getting older. I'm getting more mature. And you're like, well, you couldn't be less mature. I get that. So stat, test, chi-squared test, because it's test of independence. And I get a p-value of 0.002. That's less than, I don't know, 0.05. It's less than 0.01. But 0.0026, that's a small p-value. I'm rejecting. That's a lot of evidence, all right? So in this case, not only do I have evidence, I have strong evidence. We consider it strong evidence when we reject, all right? And remember, we always have evidence, but the question is how strong. In this case, strong enough to reject. Best answer is A, so 55 is A. All right, moving on to 56. A survey of 200 high school students is conducted to see if there's a relationship. Oh, there is a keyword. Between whether or not a student is taking AP statistics and whether the student plans to attend public or private college. The data is summarized in the table below. All right, so we have multiple categories. Chi-squared is a relationship, obviously test of independence, but what is the test statistic for a hypothesis test? And they tell me right now the null is independence, so it's obviously a test of independence. And they took one sample, and we have two variables, one sample, two variables, test of independence. The key word is independence / relationship. So we need to go ahead and enter the matrix because we need to calculate some expected values. So second matrix, edit, one, enter one, then back up. So this is a 2 by 2, 33, 77, 47, 43, stat, test. And all they're asking us to do is to set it up. We go ahead and run it. And I'm going to re-enter the matrix because I was having so much fun there. And I end up finding the first one is 44. The next one should be 66, then 36, and then 54. All right, so I should have these expected values. And basically, just so you know, on a FRQ test, there's usually enough room off to the side to write it down just like this. And this is what they would be looking for on the AP exam. If you have a chi-squared, that you put your expected here. All right, so 33 minus 44 squared, 77 minus the 66 squared, etc. If they ask you on one of these if they ask you on independence or homogeneity for the individual contributions, you're going to have to calculate these by hand, as a calculator won't do it. But remember, this would be contribution for one here, contribution for this one, contribution for this one, contribution for that one. But you would have to calculate them by hand because the calculator doesn't do that like it does on the goodness of fit. All right, number 57. That's the Lobo, last one, best one. It is hypothesized that scores on a certain intelligence test are normally distributed. Of course they are, with a mean of 100 and a standard deviation of 10. A psychologist runs a goodness of fit hypothesis on a simple random sample of 100 scores. And basically they want to know whether or not this truly matches the, whether the goodness of fit test, whether these IQs match the normal distribution. And supposedly IQs are normally distributed. So let's talk about the normal distribution and remind ourselves of something. So they're telling me this is a mean of 100. Now, one thing I remember is we go 1, 2, 3 standard deviations above, 1, 2, 3 standard deviations below. And one standard deviation is 90, and this is 110, and this is 80, 70, 120, 130, Mr. Spencer over here. And then I know something about this. I know that in this area, I have 68% of my data. So in the center, I'm expecting it to be 68%. So 0.6, so this area from 90 to 100 should be 0.68, because remember, expected value equals NP. So in this case, we have 100 scores. So 100 times 0.68. Well, that's 68 scores. If I cut that in half, I should have from here, that's half of that. That should be 34 scores. And this should be 34 scores. So my expected value from 90 to 100 is 34. Well, already that kind of gets me to my answer. But I can continue on with this. If this was 68%, what's in each tail? Well, in each tail, I'm going to take that one whole, 1 minus 0.68, and divide it by 2. And so now I have, don't know what happened there, 1 minus 0.68, enter, divide it by 2, and I end up getting 16%. So there's 16% in this tail, and there's 16% in this tail. Well, 16% of 100 is obviously 16. 16% of 100 is 16. So my answer to this one is B. Why? Once again, 68% is plus or minus 1, so 34% between. So that's 68% here. I cut it in half, so that's going to be 34% right on this side and 34% on this side. 34% of 100 is 34. 34% of 100, 34. Then we had 16% up here, 16% of 100 is 16. So my expected values are 16, 34, 34, and 16. One of my students just called me out and told me that I should have said an empirical rule. And yeah, I was using the empirical rule. 60 plus or minus 1 standard deviation is 68%. Plus or minus 2 standard deviations, so plus or minus 1 is 68, plus or minus 2, 95, plus or minus 3 is 99.7. So I was using the empirical rule to go, oh, I know 68% is centered in this, is given in the center. All right. And every year I always forget that problem, to be truthful with you. But I go, well, what do I know? I start with this, I start with empirical rule because it's easy. And then I start making the relationship. All right, number 18. The number of students taking the AP statistics at a high school during the years 2000 is fitted with the least squares regression line. The graph of the residuals and some of the computer output is as follows. How many students took the statistics in the year 2003? And by the way, this, if you're watching this at home, this is a really, I put a star by it, this type of thing that definitely shows up on AP exams almost every year. So first off, this is 2000, 2001, 2002, 2003. So this is the year of interest. All right, so this is the year of interest. And so our equation is going to be, here's my y-intercept, here's my slope. So y hat equals 11 plus 13.9826x. All right, so this is year 3, so I'm going to plug in a 3 for the x value. I turn my calculator back on. So 11 plus 13.9826 times 3, and I end up getting a y hat equal to 52.94. are about 53. Okay? Well, remember, residuals equal observed minus expected. So I have a residual of about 5. We don't know what we observed. That's what we're trying to find out. But we expected about 53. So now I can solve for my observed by adding 53 to both sides. And that gives me 58. 53 plus 55, or 55 plus the 53 gives me the 58. Okay, so I had a question back on 29. And once again, it's identifying which scatter plot could have resulted in a residual plot. So this is a residual plot, and this is my, and this is centered at 0. Now, I draw a line of best fit. Well, this is my predicted line. All of these are my y hat. This is what I predicted would happen. And remember, I'm going to have some above the data and some below. Here, every single one lies on a line. So in which case, all my residuals would be right on 0. So that's not it, because I have residuals above and below. Well, remember, residuals equal the observed minus the expected, or actual minus predicted. Actual minus predicted. So my actual here is below my predicted, so my residual would be below the line. All right, I'd have a negative because this is below what I predicted. This is a negative distance, or a negative value. Whereas when I look at this one, when I look at C, it's above the line. So this one here is going to have a positive residual. So if I were making a residual plot for C, it would have looked like this. I would start off positive, then I'd drop below the line. I'd drop below the line and become negative. Then I'd come back above the line and I'd finish up positive. All right, and B started off above the line and then dropped below the line. So as above the line became negative and then became positive again. So C and B both will have the same residual plots. These two, the residual plots, you could not tell the difference. A, though, is the one that started off negative, so started off with a negative residual and then became positive.